All right, welcome everyone. So today we're going to talk about describing and displaying data in R. There we go. All right, so anytime we start working with or managing a data set, one of the very first things we want to do is display or explore the data. And we call this exploratory data analysis. Choosing an effective data display can be difficult. Creating one can be difficult as well. But once you have something, you can really tell a great story with data. And that's what we're going to focus on today. So a couple things that I want to mention. First thing is that all of the R code that you're going to see throughout this set of notes uses two libraries, the Tidyverse library and the SCIM-R library. So these are both going to be very useful for us this semester to create both engaging and professional looking data visualizations and simplify our code to get various summary statistics. I will always include a command to initialize or load these packages at the start of any R Markdown or RStudio Cloud document. That command is library, and then in parentheses, whatever the name of the package is. Look for this in any assignments that I provide you and make sure you run it first. Second thing I wanted to mention is that all of the materials that you'll see for this class, including these slides, have actually been written in RStudio. What that means is if you take the code, copy it, load the data, and run it in RStudio Cloud, you should get exactly the same outputs. The final thing that I want to mention as a disclaimer is that throughout class, anything that will appear on the slides, I'm going to use a different color palette than the default. And the palette that I'm going to use is one called the CB palette. I've chosen this one for a couple reasons. It's a lot easier to visualize on the projector than the default. And most importantly, it's colorblind friendly. So if any of you have any color sensitivities, you should be able to see the distinctions between groupings. If you're familiar with hex color specifications, here they are. All right, let's get started. So our example data set is going to come from the U.S. County Complete data set. So this data set lives in an R package called Open Intro. It's the package that goes along with our textbook. And it contains some information recorded for 3,143 counties in the U.S. So I'll load the Open Intro library to access this data, and then I'll use a function called data to import this data into R. I can use a command called names to see all of the variables that are included in this data set, and there's 53 of them. For each state, I have their state, the name of the county, the FIPS code, these are federal identifiers, population in 2010 and 2020. I have various demographics, racial breakdowns, education levels, housing, employment information, all kinds of stuff. To get more information about these variables, we can go to the help. So in R, you can go to the RStudio console. So let me switch over to RStudio, and here's what I'm going to do. I'm going to type help county complete, and let's double check how this is spelled. R is case sensitive, so it's county with complete capitalized. I haven't initialized my RStudio library, so one thing that you'll end up running into is that if you haven't actually run a code chunk, you won't be able to access things. Now that I have that loaded, I can type in county complete. Over here in my RStudio help command, that actually brings up the documentation for this data set. So here is some information about all 53 variables. And this is going to be a nice way for you to get help both with data sets and functions in R. So speaking of functions in R, let's talk a little bit about how R actually works under the hood. So R is what's referred to as a functional programming language. Functions in R tell it what to do with a data set or variable. We use options within each of the functions to customize or to set different variables or to change some of the default commands. The essential structure is this. So we write the name of the function. This is the command that we want to use. And then various options go in parentheses. Now, one thing to mention here is that R was written initially to do statistical analyses and create graphics. So at the very beginning, R was designed in a way so that you could easily manipulate data. The capabilities have gotten a lot more advanced since then, but the structure is still a legacy of the fact that we want to center our work around programming with data. Okay, so the first major function that we'll encounter in R is the summary function, and this function summarizes a data set. So I'll type summary, I'll input the name of my data set, here county complete, and I'll get summary information. As I scroll down, you can see summary statistics for all of the variables in the data set. Here we have 53 variables, so these summaries are quite big. If we have a numerical variable, like for example, the number of private non-farm establishments in a county, we'll get the minimum, quartiles, we'll talk about those soon, the median, the mean, and the maximum. If we have a categorical variable, like for example at the very beginning, at the very end, there's a variable that I've created that's called the rural data set. That takes on what are called character or text values. So we've got some information about those. Now, if you have a large data set like we have, you don't really want to deal with this huge summary output. So we can create our own summaries instead. So for example, let's say we have a categorical variable such as this rural variable. What this rural variable does is indicate counties that have a population density less than 1,000 people per square mile. That's how the U.S. Census Bureau defines a rural area. If we want to know how many counties in the U.S. are considered rural, what we're actually looking for is the frequency distribution, the distribution of the counts in the data set. So here's what I can do. I can take that county complete data set. I can use a group by function to split it up or group it based on whether the county is classified as rural or urban, and then create a summary. So here's my summary information. That tells me that the vast majority of counties in this data set are in fact rural counties. Now, one thing that you're seeing in here is something called a pipe operator. That's what this percent arrow percent is. Pipe operators essentially work like an input. Everything that's on the left-hand side gets piped through or sent to everything on the right-hand side. Essentially, this is how the pipe works in R. So I'll play this GIF, courtesy of Danielle Quinn. She did a really fantastic job with this. Here's the basic idea. So Mario enters into the pipe and he finds his hat. So Mario stays the same as he travels through the pipe, but something gets added or something gets changed. He gets a hat. As he goes through the next pipe, not only does he still have the hat, but now he's got a fire flower. That fire flower gives him firepower. So you can see that the data in this case, or Mario in this case, gets transformed step by step as he moves through the pipe. So let's go back to this data set and talk a little bit about counting categories. So again, we're taking that county complete data set, grouping it up by rural urban status, and then summarizing how many counties are in each category. One really great thing about R is that it functions exactly like a calculator. So if I want to know, for example, what proportion of counties are considered rural, I can take the number in that rural category, 299, divide by my total sample size, 3143, and get a result. In this case, 95% of counties are considered rural. Now here you can report that as either a percent or a decimal. Either one is perfectly fine. Now there's a special notation that we'll use here. We denote this sample proportion, or the proportion in a category that we care about, as p hat. P for proportion, the hat indicating that it's a value calculated from our sample. Now we have a lot of ways that we can calculate that sample proportion. For a category, we can group our data up. Let's say we have a numerical variable that we want to work with. So in the US, 22.6% of the population is younger than 18. That's the overall 18 and under rate. Some counties must be above, some counties must be below. If we'd like to find out how many are below, we can do that by using a filter to select out or filter out only the observations in my data set where the age under 18 is less than 22.6%. Then create a summary. So 12,073 counties in the US have a lower than usual proportion of children. If we want to do an higher than usual proportion of the elderly, which in the US is about 15.2% of the population, we can use the same filter. Our filtering variable changes. We're now looking at the age over 65, and we're looking at how many are greater than or equal to 15.2. So about 1,700 counties have more than usual proportion of the elderly. With this data set, we might want to look at specifics. So we might want to know which counties have the lowest proportion of children. We'd like to look at the data to do that. However, there are so many variables that we'll need to cut things down. So here I'm using a select command to choose only the variables that I want. Here, the state, the county name, and the proportion of people aged 18 or younger. I'm then going to sort or arrange this so we'll see youngest going up. Now something interesting about this data. In Hawaii, Kalawao County has no children. There's no one there age 18 or under. So maybe we'd like to know some more about this county. So I went to Wikipedia. Here's Kalawao County. It's a county in the state of Hawaii. It is the smallest county in the 50 states by population and land area, and it has a unique history. From 1866 to 1969, it was used as a quarantine zone for people with Hansen's or leprosy. So that explains some of the unusual features of this county. Another really great explanation for that is that the population in 2018 was 88 people. So looking through the data, we might come into a situation where we want to do a bit more investigation. So here's another example. If we want to look at the counties with the highest elderly population, we can arrange in descending order. DESC stands for descending. So Sumter County, Florida is another interesting one. 43% of their population is age 65 or older, retirement age. So let's take a look at Sumter County, see what we can find out. It is the oldest median age in the US. It is made up of a lot of retirement communities, and it's part of the Orlando metro area. So that right there tells us a little bit more about the demographics of Sumter County. All right, so that's some basic data summary. Now let's take a look at graphing. The graphs that we're going to use in this class come from the ggplot function. GG standing for Grammar of Graphics. Now, ggplot has a fairly unique grammar, but is very powerful in terms of the plots that it can create, both in terms of plots that look nice and are easily customizable. Most of the plots that you'll see in the news and literature are actually created in ggplot, so it's highly versatile. The way ggplot thinks is this. So first we take a data set and we pipe or send it into the ggplot function. That's our input. Within the ggplot function, we want to set some aesthetics. These are variables that you want to plot and where. So maybe we want to plot rural-urban status, for example, on the x-axis. Going forward, anything that you want to change related to a variable happens in those aesthetics. And we'll see what this looks like next. So we'll take the county complete data set, we'll pipe it into ggplot, we'll set our x aesthetic, and this is all we get. We've created our plotting window, that's what this gray box is. We've defined our x-axis, and that's it. We haven't actually told ggplot what we want to plot yet. ggplot thinks in terms of geometry. So what are the shapes that we want to add to our plot? So for example, we can create a bar chart using the geobar geometry. Essentially, that's going to add a new bar chart layer to our plot. Anytime we're adding more layers, we're going to do that with a plus sign. So this first part created our plotting window. Now we're adding new layers to our plot. So we can see that far and away there are more rural counties in the US than urban. We can customize this by adding some labels and changing some colors. So let's walk through this and see what's different. Within geobar, I've added an aesthetic, so I want this to change based on the variable. And what I want to change about the plot based on a variable is the plot shading or the fill. So in this case, I want the fill of the box or the color shading in the box to change depending on rural status. My labels are what's specified with this labs function. My X label is rural-urban status. My Y label is number of counties. Your labels do need to go in quotes. You can use either single or double quotes as long as you're consistent with your left quote and your right quote. I use single only so that I don't have to hit the shift button, but you're welcome to use double quotes as well. And the last part of this code, the highlighted part, changes the color scheme. And again, I've set this to be a color palette that I found appears a little better on the projector, the CB palette. If you take this off, you'll get the default color palette, which if you like coral and teal, awesome. If you don't really like coral and teal, you can mix this up. The default color palette in ggplot changes depending on the number of colors that you have. As you get more and more color groupings, it gets more difficult to distinguish, especially looking at 7 and 8 colors. These greens and blues tend to run together. As we get more comfortable this semester, we'll look at more customization options, more coloring options as well, but you're welcome to use the default color scheme if that speaks to you. Okay, so let's talk about graphing numerical variables. And there's 3 major types of plots that we might use for a single numerical variable: histograms, box plots, and then scatter plots. We'll actually work with 2 numerical variables. So let's say that we want to describe the distribution of high school graduation rates in the US. So how many people in a county are graduating from high school? We could create a histogram. So this is our histogram geometry. It looks like we are seeing lots of counties that are graduating somewhere between about 80 and 95% of their population from high school, which is pretty good. So here we've got our histogram. The way this histogram is created is by taking the range of the numerical variable and splitting it into bins of equal width. So if we take a look at how many bars there are in this histogram, we should count 20. Some of them are very, very small. R is smart with how it assigns axis widths. It will not go beyond the boundary of the data unless you tell it to. So this very faint gray line indicates that there is still some data over here on the left. There is still some data over here on the right. If we add each of these up, there should be 20 splits or 20 bins here. So we'll count how many observations fall into those subgroupings, and then we'll draw a bar for each one. The height's going to correspond directly to the number of observations in that bin. So here, this is a little different. I've changed the number of bins now to be 15 instead of 20. We see some wider ranges here for the bins. Overall, the same basic shape. In most U.S. counties, between 80 and 95% of people have a high school degree. Now, things that we want to look at when we're looking at histograms. We care about the center, so we care about where the middle values in the histogram are. We care about the shape. What does the distribution actually look like? We care about how spread out it is, and of course we care about any unusual observations. We want to try to explain those weird data points or those outliers. There are some common shapes that appear in practice, and here are some examples of 4 shapes that you'll often see. So in the upper left-hand corner, this is an example of a bimodal histogram. We have a peak of data here on the left, and we have a peak of data here on the right. So there's 2 major modes to this data set. The upper right-hand graph shows an example of a unimodal data set where the major peak or major concentration of the data is just here on the left. This plot's also an example of a data set that we would consider to be skewed right. We have a peak here on the left-hand side, and then the distribution sort of tails off to the right, or skews off to the right. We can also have a skewed left plot, which would just be the mirror image of this. The lower left-hand plot in green is an example of a symmetric distribution. Things are roughly the same on the left and the right. Now, we're not seeing perfect symmetry, and that's okay. It's nearly impossible to get perfect symmetry with a data set. But overall, we've got pretty similar patterns on each side. And then finally, if there's a fairly flat distribution or you're not seeing any major patterns on one side or the other, everything looks about the same, pretty flat, we refer to that as a uniform distribution. All right, so let's talk about interpreting these histograms. The other thing that we look for are outliers. Are there any unusual or weird observations? Outliers can be much smaller than the rest of the data points, or they can be much larger than the rest of the data points. Now, I will say that there are different tests that you can do. There's certainly some described in your book. Most of the time with outliers, you know them if you see them. So you're looking for really extreme or unusual differences. So, for example, if we take a look at the distribution of poverty rates in the U.S., this distribution is unimodal. There's one major concentration. A lot of the data is between about 10 to 20% for the poverty rate. There is a definite right skew to the data as well. You can see this sort of trend off to the right. If we look a little closer, so now I'm going to filter out and only look at Nebraska. So I'm looking for state exactly equal to Nebraska. I've also changed the color, the shading here to red to illustrate that you can just type in a color name, and also red and Nebraska go together. Here we have an outlier. There's a county in Nebraska that's pretty different than the rest. So we can look for that county by filtering out from the data, state Nebraska, poverty rate greater than 25%, and we get that county back being Thurston County. Now, I know most of you probably aren't from Nebraska. Thurston County is a little bit different from the rest of the Nebraska population. Thurston County is in the very northeastern part of the state. It borders the Missouri River. Thurston County is home to the Omaha and Winnebago tribe reservations, and that makes up the majority, or the entirety, of the county. So Thurston County is pretty different from the rest of the population in that it is a reservation. Okay, So now that we know a little bit about histograms, let's compare those to box plots. So box plots are another way that we can plot or visualize numerical variables. Here's how they work. So we draw a box, and this box represents the middle 50% of the data. The lower end of the box represents the first quartile, the bottom 25%, where that cutoff lies. The third quartile, or the top of the box, cuts off the upper 25%. And then you'll see a dark, thick line in the middle of the box. That indicates the median. This is not the mean. The box plot has then lines that extend out of the box known as whiskers, and these extend to either the maximum or the minimum observations. Any outliers will be indicated with a dot. So, for example, here are two box plots. These are side-by-side box plots of the poverty rate in the U.S. We've got it split up by rural and urban communities. So for urban communities, 50% of those counties have a poverty rate that's somewhere between about 9% and about 17%. The median looks like it's somewhere in the 14% range, and there are two outliers in the urban counties. For rural counties, the poverty rate's a little bit higher, generally between 15 and 20%. The median's a little higher as well, looks like that's about 16%, and there are more outliers, more communities in extreme poverty. So, make a prediction. Is there a relationship in the U.S. between poverty rate and high school graduation rate? We think there is. Most of the reports that we read do indicate that that's the truth. Let's see if the data supports this. Generally, yes, there is a relationship. As the poverty rate in a county goes up, high school graduation rates tend to go down. To create this, what I've done is placed poverty on the x-axis in my ggplot, high school graduation on the y-axis, and then I've added a new to us geometry called geom_point. So we're drawing dots at each of the data points. Labels, again, poverty rate on the x-axis, high school graduation rate on the y-axis. As you become more and more comfortable with creating plots using ggplot, I would like to see these axis labels and working toward more professional looking graphics. So when we're looking for relationships between variables in statistics, we don't automatically jump to two things being correlated. Correlation is a term that gets used a lot more often outside of statistics than it actually does within statistics. And that's because it has a very special meaning to us. It describes a special type of relationship or association. In general, two variables that are related in some way, we refer to as association. So there's some relationship, could be one of lots of different types of relationships. So if we want to take a look at a county's high school graduation rate versus median income, here we have a clear association as well. As high school graduation increases, so does the median income. But it's a different type of association than the one that we had seen previously. In general, there's two types of associations that we'll look for with numerical variables. We'll look for a positive association or a negative association. So a positive association indicates that there is an upward trend in the data. As X is increasing, Y also tends to increase. We see sort of an upward diagonal in this example. A negative association indicates a downward trend. So as X is increasing, Y is decreasing. And this is an example of a pretty strong negative association. Now, if we want to compare or investigate relationships, one thing that can be really helpful for us is to break the data up into smaller groups. Now, there's two additional commands that I'm going to use here, and you'll explore what these do in your first RStudio Cloud project. The first is facet wrap rural, the second geom smooth. So facet wrap, what this does is split or group the data up In this case, we're going to split it up by rural status and actually create two separate plots. The second, geom smooth, this adds a smooth line geometry. And the method that we're going to use here is a linear model, a flat line. So here we see the relationship between high school graduation and median income for rural versus urban communities. There are a lot more rural communities than there are urban in the U.S. In the U.S., there is a steeper trend. So increasing high school graduation is associated with a much steeper jump in income than in rural communities. We're also seeing some differences in graduation rates. So high school graduation rates for urban communities start at about 70%. For rural, starts at about 50%. So there's some very stark differences between these two types of communities or counties. So the next thing I want to talk about are numerical statistics or summary statistics. These just give us a snapshot of some features in the data. Two that we often look at are the sample mean and the sample median. So the sample mean is the average of all individual observations. We'll denote this as X bars, so the bar over it indicates that we're looking at an average of a variable X. The sample median is just the middle observation, so sort your data from smallest to largest, pick the one in the middle. I like to use M to denote the median. So we can find the mean and median high school graduation rates in a few different ways. So my first option might be to take this county complete data set, pipe it into a summarize function. Summarize calculates summary statistics. In this case, I want the mean and the median. So the mean graduation rate is 83%, which is pretty high. The median, 84.6, so a little higher than the mean. I can add another step in my pipeline. So let's say I want to split this up by rural and urban communities. I can add group by rural first, and then see that there are some differences. In rural communities, the mean high school graduation rate is 83%. In urban communities, it's a bit higher, 86.2%. Now, let's say I want to add some more. I can keep adding statistics to the summarize function. I can calculate the minimum, the quartiles, the medians, the maximum, and the mean, and get something out like this. This is a lot of work for a table of summary statistics. Usually in this class, if it looks like there should be an easier way, there will be an easier way. So the easier way, the one that I like to use, is something called the skim function, and this lives in the skim-r library. We'll load the skim-r library, select the variable that we're interested in. So here I want to select high school graduation, and then I'm going to just skim it. So this tells me a lot. It tells me that I have a numeric variable. None of the observations are missing. If there were any blanks in my data, this would let me know. 3,143 observations are complete out of a total sample size of 3,143. The mean is 83.1. The minimum, or P0, is 47.9. First quartile, or P25, this cuts off the lower 25% of the data, 78.4. Median, 84.6. Highest 25% of the data, 88.6, and then P100, the maximum, is 99.3. There's one statistic that I skipped here, and that's SD. Let's talk about that one. So SD stands for sample standard deviation. So this measures how spread out the data set is. Standard deviation really tells you the typical distance between an individual observation and the sample mean. It's calculated in kind of a weird way. Step by step to get the standard deviation, what's happening is that we take an observation, subtract away the mean, we square that distance, add them all up. After we add them all up, we divide not by the sample size n, but by something a little different, n minus 1. Then we take the square root of that. There are a lot of steps to calculating standard deviation, and I won't ever ask you to do it by hand, but it is good to kind of know where this number is coming from. the larger the standard deviation gets, the more spread out the data actually becomes. So large standard deviations indicate that observations are far from the mean. Small standard deviations indicate that the observations are closely concentrated. They're all very similar. Why do we divide by n minus 1? That's something that a lot of students find tricky. The idea is this. We want to get the best estimate that we can of the population standard deviation, which I'm calling sigma. Dividing by n minus 1 instead of n gives us a little better estimate. We tend to get a closer number to the population standard deviation. So that's why we divide by n minus 1. One thing that you'll see pop up from time to time in our output is another summary statistic called the variance. The variance is just the standard deviation squared, or alternatively, the standard deviation is the square root of the variance. Variance has some really nice mathematical properties, but it's not on the same scale as the original data, so we don't tend to use it much when we're working with data. If you do go on to take higher level stats or math or data science courses, variance is really useful in probability theory, so you may encounter it again. So what can we say about the variability of high school graduation rates? Well, one really nice way to think about standard deviation is that it's the distance from a typical observation to the mean. So a typical county might be about 7 units away from the mean. So a typical county might have a high school graduation rate somewhere between about 76% and about 90%. We would expect most of the counties in the data to fall between those two values. Now, that's not the same as the distance between the quartiles, but it's a pretty good estimate or a pretty good range for where most typical counties will fall. We can also use standard deviation to compare. So let's take this skim, group the data up by rural-urban status first, so we have a nice little split of rural versus urban. Rural being the top row, urban being the bottom row. It looks like the rural data is a bit more spread out than the urban data. The standard deviation for rural counties is a bit higher than the standard deviation for urban counties, and that reflects the spread of the data. Again, if we look at this a bit bigger, expand that histogram out, we can pretty clearly see that there are more differences in the rural counties. There's a wider range, there's more variation. So this should be a higher standard deviation. So that makes sense. One thing that can help us, and you should have the code for doing this in the notes. If you notice, there's a lot fewer urban communities. There's an option that I can set inside the facet wrap command called scales that will make each of these separate histograms or separate plots have different axes. So now we have a different scale and we can more clearly see the differences in the shape of the variables. So sometimes it's to our advantage to change those scales. Now's a good point for a word of warning. Looking at these summary statistics doesn't tell us the whole story. It doesn't tell us about the shape of the data. It doesn't tell us about the outliers. It doesn't tell us if there's anything weird or anything interesting. So looking at these summary statistics like the mean and standard deviation is great, but we should accompany that with a visual. We want to see what the actual data looks like as well. Okay, so the last major topic that I want to talk about is association, and specifically association between two categorical variables instead of two numerical variables. So, for example, the Census Bureau stated that people living in rural areas are more likely to own their own homes. So, what I did was look up the home ownership rate in the U.S. Overall, about 64% of people in the U.S. own their own home, and I wanted to see whether rural counties were more likely to hit that bar. So I first took my data set and I added a new variable using the mutate function. My new variable, if homeownership status is more than 64.8%, there's higher homeownership rates. Otherwise, or else, there's lower homeownership rates. So looking at that, I was then able to group my data based on both this rural status and whether or not they have high homeownership rates, and then summarize with those two. So we have rural or urban, higher or lower homeownership, and then the county counts. Now, when you've seen these contingency tables before, they've probably looked more like this. Good news, we can make our table look a little more like this. We can spread our table out, so I'm going to spread out the home ownership variable. So instead of having home ownership all stacked like this, I'll have higher and then lower. I'm going to fill in the inside of the table with the counts or with N. So here we can see that there are 2,699 counties that are rural and have higher home ownership rates. So we can plot this data in a stacked bar chart. Here's what we're seeing. So for rural counties in the US, home ownership rates, most of them have higher than average home ownership. Urban counties are fairly evenly split, and in fact, it looks like there are more counties with lower home ownership rates. We could also use a facet to split the bar chart into multiple graphs, so a slightly different way to represent this data. For those counties with higher home ownership rates, the vast majority are rural. Or we could just put all of that on the same graph and dodge the position, so put the bars next to each other. All of these visualizations contain the same information and tell the same punchline. It's really just a matter of which data representation you prefer. There's lots of different ways to create this. That's true whether you have categorical data, numerical data, or any combination thereof. How do you choose the right plot? There isn't a right plot. There are good plots and bad plots though. So we'll talk a lot this semester about how to make informative visualizations of data sets, ones that give us some valuable information. So in your notes, I've provided a few more examples. I want to talk through what you should be seeing in the code that goes along with this. So for example, how many counties have increased their population? So in the ggplot function, there should be an x aesthetic, x equals population 2000, y equals population 2010. It looks like we're faceting this by rural-urban status and changing the color by rural-urban as well. One thing that I might do is take a look at change in counties. So change is going to be the difference between population 2010, population 2000. I'm dividing that by population 2000 to get a percent change now. So change is a percent. Growth, yes if we increased, no if we have a decrease. So how many counties have increased their population? It looks like the mean change, so the average increase is about a 5% increase. Some counties have changed by about 0.7%. The highest is a near doubling, increasing by over 100%. We have some missing variables. So there are 3 counties that are missing the population in one of those 2 years. For growth, it looks like most counties in the US increased their population, about a third decreased their population. Now, are counties that are growing better off? Are they measurably different? So here we're looking at poverty rates versus high school graduation rates. There's less of a clear pattern. So even though the counties in blue have increased their population, we still see that negative relationship between poverty and high school graduation rates. So at this point, what I'd like you to do is hop on over to RStudio Cloud give your first RStudio project a try. Our next class meeting after this will be on Tuesday, January 30th. That's also when your first RStudio Cloud project is due. If you have any questions between now and then, let me know, and I will see you shortly. Have a great day.